Physics. Okay, so welcome back to our course on the fundamentals of attosecond science and technology. We bring this from IIT Madras and IIT Tirupati as always, and this is now we are into this section on nonlinear optics. So the nutshell is probably growing in size as we discuss. It's a little more than a primer. We want to learn the essentials of nonlinear optics or NLO as it's often abbreviated as, and this is the basis for learning about harmonic generation and the related science, right. So, we had 3 lectures by our colleague in the previous week. So, I hope we convinced you in those sessions that attosecond science is a more extreme form of nonlinear optics. It is extremal nonlinear optics, where you just do not care about restricting the nonlinearity to low order. We just push it and say, okay, let everything break loose and we will just crank up laser electric fields and see what happens, right. So, that is very fascinating, and we realize that the physics that unfolds undergoes a phase transition, if I may say so. The physics of low order nonlinear optics is fairly foreseeable from the perspective of taking any atomic molecular system, or you can say even condensed phase, but let us say atoms, molecules to start with, which is the case that we investigated, and we just said, okay, we know that there is interaction with an electromagnetic wave, and we also understand that this motivates a perturbative treatment, and we do that. And then we immediately see that as a consequence of perturbation, we have non-harmonic or anharmonic responses coming in. But one needn't have come to optics or quantum mechanics to see that, right. Mechanical systems, the first, you can say, one of the first physics problems that any student solves very early in one's learning, which is even before you enter a university, involves such a system where you had a mechanically bound system like what we call a spring mass, and we encountered a case for going beyond the linear, at least, even if you weren't told at that time that it's a nonlinear response. It was something extra linear or beyond linear that we encountered, and things stopped there, as they should in a good pedagogic exercise. But in the case of also the next important oscillatory problem that one learnt about was simple harmonic motion, where the so called pendulum is made into a simple pendulum by a simple approximation, where the sine of theta is equated to theta because we want to keep theta small, and then it becomes harmonic, right. But I think then and there we were told, or we teach, saying, look, if it is not, I mean, if your theta, which can take in that case any value from 0 to pi over 2 on either side of the 0, you indeed need to expand the sine theta term into quadratic, cubic and higher orders of theta, and that we say is something we do not solve in the first iteration, but in subsequent cases we must have encountered, maybe we do encounter in masters level physics about how we can how to treat this problem, either analytically through methods or very often numerically, where you can simply integrate out the equation of motion and say, okay, I will involve the theta square term and then do it, or put in the full sine of theta and increase the range of angular oscillation and then look at the solutions. This one may even have done as an exercise. So, these are all very early manifestations of nonlinearity, which we are now developing in an optical context or in the context of light matter interaction, where light very often is emission from a laser, right. All of this is covered in a very nice way in Boyd's book, one of the bibles of this subject. There are also equally good books, the ones by Yarev and also books by Tyagarajan and Ghatak, and we will continue to refer to books on femtosecond and attosecond pulses and optics, as well as the a book on another stalwart effort, which is the book by Born and Wolf, and thanks to Professor Trebino for his inputs. So, in today's lecture, about another 70 minutes or so, we will have a very quick recap of the basic foundations which we laid in the earlier lecture, where we understood to a large extent the physical origin of what we can now say the real and imaginary parts of refractive index, as well as the origin of optical nonlinearity and what motivates the need to think about this aspect in optics. Right. In today's lecture, we will continue where we left off in the previous set of lectures to encounter harmonic generation, but now in this course we should start qualifying this better by saying we will look at low order harmonic generation, not high order, because we have already delved into or made a foray into high order harmonic generation or HHG. So, this should have been called low LHG or low order harmonic generation, which we do not in literature. We just call it harmonic generation and imply, and often by defining it by context, we imply sum of frequency, sum of difference frequency generation of various kinds, right. In today's class, we will also go into learning about the application of a very basic physical principle and tenet to this process, which is energy momentum conservation, which manifests in what we will also call phase matching. I hope we can cover all this today. If things spill over, we will carry it forward to tomorrow's lecture, the second lecture for this week. Okay, quick recap: pulses, optical pulses. I say this and I hope this is the image that flashes in our minds now, right. But then a very decent picture of what happens when an atom encounters light. It sets dipolar oscillations into motion. This leads to both refractive or phase modification phenomena as well as absorptive phenomena. Absorption is visible in absorption lines, which we have encountered several times in earlier discussions. But to formally treat what light does to matter, treating matter here in this case, since we looked at a quantum mechanical treatment in the previous set of lectures, we are still in this section confining ourselves to a classical model where the atom is nothing more than a forced damped oscillator driven by the Lorentz force of the incident radiation, leading to a displacement xe between the centers of charge of the point like nucleus and the electron cloud, which leads to the formation of a dipole. Here we have considered at least in this cartoon a spherical electron cloud. It need not even be so, but this displacement as a function of time when driven by this harmonic field, sinusoidal field, essentially oscillates, produces oscillatory motion of this dipole at the same frequency as that of the incident driver or the light wave here, and a term, a complex coefficient to this oscillation. Remember that both the electric field of E of t and this displacement are real quantities, okay. But then we are using a complex notation and hence these are complex. So, this means both amplitudes and phases are both involved and play an important role, right. So, typically depending upon whether the driving is under damped or over damped about the resonant frequency omega naught is the natural frequency of this atomic system which is being driven, okay. We also call this the eigen frequency, the resonance frequency and so on and so forth. These are all synonymous phrases describing omega naught, whereas omega without the 0 or naught in the subscript is the frequency of the driver or the electromagnetic wave. Now, the damped force oscillator solution for light driven atoms, which is what we consider here, can be explored and examined as a consequence of 3 different cases of the relationship between the resonance frequency omega naught of the atomic system and the driver frequency omega naught. If omega is much less than omega naught, then xc, the displacement, okay, is pi out of phase or 180-degree out of phase with the driver, and if it is if the driver's frequency is far greater, then the electron oscillates in phase, whereas if they are at resonance, then the oscillation is a pi over 2, albeit with here a negative sign. It is pi over 2 or 90 degrees out of phase with respect to the driver. Okay. These are the 3 hallmarks of the way the atomic system responds in this case when driven by an electromagnetic wave. But note once again that the response of the atomic system, okay, the oscillations themselves are still at, in terms of their time dependence, at omega, the frequency of the driver. Omega naught merely marks one important location on that scale, right. When if the frequency of the driver and the driven system match, then the amplitude of oscillation is rather large for the resonant case, okay, as compared to the 2 off resonant cases. That is all this signifies. There is no change in the frequency of the oscillation of the electron cloud or the atomic system as compared to that of the driver. So, this is what we model in this case. As you see, both above and below resonance, the amplitudes of the oscillation, amplitudes of xc of t, are significantly lower. That is what we want to note here. Now, the frequency response of the atom, okay, which has nothing to do with the time dependent part, but the coefficient that precedes the time dependent e to the minus I omega t in that expression, is essentially dependent on 2 factors native to the atomic system: omega naught, the resonant frequency, and gamma, the damping constant. Okay. It depends on these 2 factors. This gives us a frequency response which we sketched very elegantly earlier as a function of delta. Delta is the detuning of the driver with respect to the natural eigen or resonance frequency of the atomic system, omega naught minus delta, right. Now, the function 1 divided by delta minus I gamma is the complex Lorentzian, which can be broken down into a real part delta by delta square plus gamma square, the real part which is an odd function of the variable delta, whereas of course, gamma is fixed, it is not variable, and the imaginary part which is an even function, and it plots like this. So, the imaginary part is a nice Lorentzian curve, the way we are used to defining a real Lorentzian, which is a function. If it were to be of x, then this has the form of something like 1 divided by x square plus a square, where a is a constant. It is an even function of the variable x in this case, and in the case of the real factor, we have this has an x by x plus a square form, or here delta by delta square plus gamma square. This is the classic, if you like, S or Z shaped curve for the real part. This enables us now to answer the question, having examined what light does to matter, what matter does to light, that sort of give back we are now in a position to accurately physically model this aspect, where we now have the light wave propagating through a medium, okay, with an incident electric field amplitude E of t at the entry point z is equal to 0 or z equals 0 in the medium, and we are often interested in knowing the consequence of this medium of length L, leading now to a modified electric field at x or z, in this case z not x, equal to L as a function of time t. This must have undergone some modification unless this box were to be empty, and the total electric field at any intermediate point in the medium, which is something we are very much interested in the physics of this problem, is the sum of the incident field and the phi and that of anything, any wave that is emitted by the oscillating dipoles in this medium. So, the total field is indeed a sum of these two, which is captured in Maxwell's equations and particularly in the constitutive relation, which reads D is epsilon naught E plus P, where P is the polarization field inside the medium, which is the dipole moment per unit volume inside the medium, and E is sort of the applied field, the incident field. So, it is this expression that we got to keep in mind apart from the 4 important Maxwell's equations, which in this case we will consider for a scenario where we have no free charges or free currents either, as well as for media which are non-magnetic, which essentially means that the M vector field is a 0, constant 0 field, and therefore, B and H just vary by a factor, not just mu naught, but there could be another material factor which comes in here, but essentially no dynamics is induced by the magnetic part in non-magnetic media. You can very well consider scenarios where there is some appreciable magnetic response, but we are almost never going to go there in this course, but it should certainly be of interest to a student of science interested in such media. So, but write this down anyways, acknowledging D is epsilon naught E plus P, and then we realize that the P, the polarization field, okay, essentially appears in this manifestation of the wave equation here captured only in 1D in space, which is the Z dimension. We can generalize this to 3 dimensions. However, if we keep everything linear in terms of the polarization of the electric field, okay, for a lot of scenarios, but not all, we will actually break this convenient condition very soon. It would be sufficient to consider one space plus one temporal dimension and write down this scalar equation where we have d2 by dz2 minus 1 over c0 square, c0 being the in vacuo speed of light, multiplied by the second derivative of the electric field, which depends on time, being equal to the mu naught multiplying the second derivative of the polarization field with respect to time. Recall that in very early considerations of the 1D wave equation, we had 0 on the right hand side. So, 0 on the right hand side gave us what we were happy calling the homogeneous wave equation. Okay. So, that described purely propagative scenarios where the medium was just a passive participant. Okay. At best, in that scenario, we could have included a modification of the propagation speed of light. Okay, but there we were interested in other things such as creating wave groups or forming pulses and matters of that kind. So, we did not bother about material response over there, but now we are we have moved our focus to the response of materials in this case. In fact, in last week's lectures you had a complementary scenario where we ignored propagation and devoted about 6 hours just to dive deeper into the material response, which is the polarization field. All you did, if you wish, was simply to understand at almost without any limits on the order of nonlinearity how to compose and solve the problem of what happens to P at large light intensities or field amplitudes. This is what we endeavored to do in the previous week's lectures. But now, in this case, we are not going limitless with this equation would apply even for high orders of nonlinearity. Okay. This equation has no restriction on how nonlinear the interaction is. On the other hand, we are just developing a general treatment for how to handle this scenario. Okay. However, in this case, in what is going to follow right now, we are assuming still to be in the regime where only linear response occurs, in which case I can conveniently do the following. I actually take P of t and write this down going by its definition of being the dipole moment per unit volume by writing first the dipole moment down, which is E, the charge of the electron, times the displacement between the positive and negative charge centers xc as a function of time. Okay. Here everything is linear, and I am emphasizing that for very good reason, multiplied by n, the number of such dipoles per unit volume that we need to consider in this scenario. If we do that, then we write down the expression where we replace xc of t with the frequency response that we just discussed, multiplied by the driving field. So, the frequency dependence is all contained here in E, and even the rest of the terms, there is no reason to go beyond the linear. This is just an amplitude response, right. And here we introduce for the first time the notion of a susceptibility. We looked at very high orders of susceptibility in the previous lecture, whereas now we have just introduced in this case the linear susceptibility. So, this is chi superscripted 1 or linear chi of the linear processes that we have to consider. But what this does in the current context is to write P back in terms of one material property chi, which depends on frequency. Its frequency dependence comes about from the frequency dependence of xc, the frequency response of xc, and then we get a very nice expression where the right hand side of this inhomogeneous equation is merely a factor of chi multiplying d2e by dt2. If we do this, we work ourselves into a scenario where we now retrieve, okay, the wave equation back with a new velocity factor, which is 1 over the square root of c naught divided by the square root, 1 over the square of c divided by 1 plus chi. So, 1 plus chi plays the role of conventional refractive index. So, this is just in this case, this merely becomes a propagative effect where the wave velocity is modified by some factor. That is all we have learned from this exercise, right. Remember that in this scenario we deleted all free sources of charge and current. Okay. So, that of course has a bearing in arriving at an equation like this, which we would not have been able to do if we had any kind of like free sources. But this is a very good approximation, not approximation, a very good physical model for a lot of scenario where we involve dielectric media, even metallic systems for that matter. Now, we therefore track this down to the real and imaginary parts of the refractive index, the real part being responsible for refraction, the imaginary part for absorptive phenomena. For the imaginary part, the absorbance alpha of the field, which essentially attenuates the electric field by a factor exponent minus alpha by 2 multiplied to z, the propagation variable, is essentially related to the imaginary part of the susceptibility, electric susceptibility chi, and the refractive index itself is the square root of 1 plus the real part of chi, but the square root here we approximate this to the first term of the Taylor expansion, making it a half, which we may or may not always want to do, but this gives us a neat expression expressing the refractive index as a linear function of the susceptibility, right. So, now a typical dispersive medium, okay, considering only the real part of the refractive index, which we generally are used to calling the refractive index with the popular symbol n being ascribed to it, is plotted here over a range of frequencies going from infrared to X-ray, okay, where the real part has these characteristic z shapes manifesting in its plot, and in regions where the refractive index grows with frequency, we have what we usually call normal dispersion, and there is a small region of opportunity at frequencies greater than the resonant frequency in every case, where the refractive index essentially even falls with frequency, leading to anomalous dispersion, but there we are close to absorption as well taking place, okay, but we know that we need even anomalous dispersion, right, for certain applications where we want to do some dispersion management in a propagative system with pulses.